I will get started, and please interrupt whenever you have questions. I think it's better to also have a discussion in the process. So that's on to a local institution. When he was alive, he was just financing it a bit like a mini Bell Labs or IBM research center, just researchers doing whatever they wanted. And now we try to keep a bit of that spirit going. That's rare nowadays. So fellows like myself, we get 5 years of more or less unlimited funding to do whatever crazy science we want to do. And we are also allowed to switch direction if needed. Right now we're hiring about, well, this year is 0. So 0 to 2 fellows per year, depending on the year, of course, and the situation. So in this talk, you will see a lot of like these two-dimensional like conceptual graphs. I think it's a good way to visualize things. So in this particular example, I'm trying to represent different fields of study as the length scale they're concerned with, and also the degree of interaction complexity that they deal with. And at Rowland, we cover a lot of the two-dimensional space. My group in particular, we work on nanoscale sensors and the imaging technology. But since about 2 years, I've been looking into a much bigger problem, a very interconnected problem, which I call civilizational habitat engineering. I think it's a very urgent problem, and the reason of its urgency I will discuss later in the talk. But before, I'd like to tell you a bit like how I think as a scientist engineer. I think it's very fruitful to have your research driven by a very set target, a very specific target, a very high and aloft vision of some sort. So in my previous work, before I really switched direction to climate, I was trying to make a microscope based on atomic force microscopy and MRI principles, basically use the probe to locally take MRI signals of matter. And most isotope have nuclear spin, so you can make an MR active versions of most compounds. So it could be a that technique that can give you 3D images of any like small pieces of heterogeneous matter. So that's very useful in material science, where many things are heterogeneous on the nanoscale, and when you're looking at individual copies. So that's been a very fruitful target to aim at. So for example, we had to develop new methods to make single crystal diamond cantilevers. These are very good sensors. We were able to make them up to like several hundred microns long, but down to like 50 nanometers thick. So that was a pretty like satisfying engineering feat at the end. And more recently, when you're trying to make a microscope that has high resolution, you also want to be able to like machine tiny devices with high precision. So we are currently developing a nano machining technique where you can carve out individual layers of atoms. So basically machining with atomic resolution. So that's a field or an experiment we were very actively pursuing before the pandemics, but now, I mean, since almost a year now, the students were all sent home, so nobody's working on that. So we have more or less switched to theoretical investigations. And if you're interested, we also have a method to grow metallic, I mean, it's generalizable, nanowires with any design crystal orientation along the nanowire axis. So so this example are 3, 2, 1 nanowires along the nanowire axis. So that's if you're interested, go look at that paper. It's quite it's interesting from a theoretical point of view, how that can be achieved. And another work is there's a method to pick up single nanoparticles if you add a handle onto them. So in this case, these are 10 nanometer iron nanoparticles that you can attach to, in this case, a titanium handle. Then you can use standard like micro manipulators in the SEM to then handle individual nanoparticles. So the original focus was really a well-chosen target, and we were very much on our way to reach a single proton imaging and sensing sensitivity by the middle of this coming decade, if everything happened according to plan. But obviously, the world is on fire, and it's already depriving a lot of our friends in other parts of the world from having a stable livelihood, and people are forced to move. So researchers who are tasked with providing a better future for humankind, we shouldn't be stuck in our little worlds and just continue doing what we have been doing. So I like to, again, return to this sort of 2D visualization, but this time let's look at what threats are we confronting. You hear about like sea level rise a lot when we talk about climate change, but if one really delved into the scientific literature, you would find that sea level rise is a pretty predictable phenomena, and if it's predictable, you can assess its impact. And sea level rise impact most coastal infrastructure and cities and some island nations, and cost estimates for that are in the hundreds of billions of dollars, which put into perspective of how many trillions the COVID has, brought upon the world. It's a rather manageable problem. So it would be wrong to focus or really use sea level rise as justification for confronting climate change. Ocean acidification, which fewer people know about, is a bigger problem because it, from a conceptual point of view, it impacts a three-dimensional space, which is most of the volume on this planet surface, and that has the potential to wipe out entire ecosystems and fish and coral reefs and all the calcifying organisms. So that can impact many more people, and consequently is more troublesome. And ocean plastics also gets a lot of media exposure because they tend to hurt or generate striking images. And humans are unfortunately visual creatures driven by what we see, not really are able to comprehend that the biggest threat to our very existence in the very near future are these thermal extremes that are projected to become 10 to like 80 folds more frequent in the coming decades. And we are already witnessing many of the well understood mechanisms by which our food system and academics can become rampant. And we humans as animals, we are, we depend on food. And when these systems collapse, we will disappear soon afterwards. So while like material science and nanoengineering is like a great personal passion of mine for the past 2 decades, I think the urgency of providing humans with a livable planet is a much more urgent issue. And top of the list is also educating the next generation of young people who will be actually carrying out a lot of the engineering solutions that my lab and many others are trying to design. So today, I will again highlight how urgent the climate crisis really is in a more precise time frame. And I will try to show why renewable energy, the pursuit of renewable energy, and the belief that it's a cure for climate change is a myth, and a very horrible myth that's paralyzing our civilization. Then I will try to talk about the solution framework that we have come up with, and why it's important to first get the thermal runaway effect under control before we even consider CO2 drawdown due to the kinetics of these different issues and their urgencies. All right, so another 2D plot as promised. So as a material scientist, we are very familiar with phase diagrams, right? So I'm trying to use the same analogy, but in the context of ecology. So in the green area, I'm plotting a region of Earth CO2 concentration space and the surface temperature region where the current ecosystems can thrive. And the method by which I found that region is by looking through hundreds to thousands of papers on ecology. So on the left side, we know that plants on Earth need some minimum level of CO2 in order to perform photosynthesis, because CO2 is the starting material for sugar making. On the right side, however, many animals become disoriented and show signs of a toxicity when you put them for a long time, above 1,000 ppm CO2 concentration. And the short-term effect can be observable at about 2,000. So we shouldn't really go over that boundary of 1,000 to 2,000 ppm. But anywhere in between, there's no measurable effect for animals. Like in rooms, like right now we are all locked indoors. We actually access that region pretty frequently. So please open your windows when you feel you're, a little tired. On the temperature axis, the first, 1 degree seems to be like a good experimental parameter to use, and people have studied that. And locally, one can already observe species disappearing locally when you experimentally subject like plants to sustained 1 degree Celsius increase over several years. And experimental studies on animals at 2 degrees has, in all cases that I've seen, certainly above 95% of studies show consistently negative effect on multiple life stages of the animal. And at 3 degrees C, many papers are continuing to be published that use the term biological annihilation by mechanisms that include individual species collapsing, and then the organisms that depend on their existence also collapse as a result. So this domino effect pretty much guarantees at somewhere between 2 to 3 degrees Celsius, we're looking at the collapse of the system, at least the complex organisms that humans depend on, which includes crops for that matter. So if we conceptually decompose these two threats and put them on the same temporal axis defined by the current trajectory of CO2 and consequent temperature increase, we find that we are coming right up against the thermal tolerance threshold in the next 10 years, and certainly not more than 40 years from now. And interestingly, even if we consumed all the fossil fuel that's proven in our reserves, we will not even get close to the intrinsic CO2 toxicity effect for animals. So that puts into perspective that we should perhaps not focus so much on calling CO2 drawdown or stop to emit gases, but really look at the temperature threat head on. So now we're ready to discuss why renewable energy and their pursuit is futile at the current moment. And worse yet, we cannot let go of fossil fuels safely. So as the smoke stack showed in the previous picture, we emit more than just a pure CO2 when we burn fossil fuel. We have volatile organic carbon, we have NOxes, nitrogen oxides, and we have sulfur dioxide. And together, these compounds mix in the and react in the atmosphere driven by sunlight, by photochemical processes, and they form nano particles, which have two functions. One, they directly change the direction of flight, scattering a lot of the incoming photons back into space. Second, they also promote cloud formation. They act as condensation nuclei. So the net result is that, especially in regions that are high emitters, they form a blanket, a sunshade over the Earth. So averaged over the Earth, we're looking at about 1.6 to maybe 1.2, so somewhere 1.5 watt per meter squared of cooling averaged over the Earth's surface. So this last paper is just came out this year, and it's a meta study of past 40 years of data and experiments. So we can ask the question, okay, for this amount of heating power density, what's the impact on surface temperature? we can estimate that from either paleo data, so that's a slope derived from where Earth was in history. That's roughly gives you like 0.8, 0.9 degree per watt per meter squared. And more recent estimates are based on model studies are in line with this historical data. So the reason why there might be a little bit of discrepancy could be that this slope is actually a function of where the Earth is. So the hotter it is, the more sensitive the Earth becomes. So since we're talking about in the future where we haven't been in the past as much, it's very possible that the slope gets tilted up a little bit. So model studies are, so I guess experimental and model studies are consistent. The bottom line of this analysis is that if we stopped all fossil fuel emissions, we lose all this cooling, then the consequent warming would be the product between how much power you are exposing the Earth to how much temperature changes as a result of that power. And it's not hard to see that we're looking at between 1 to 2 degrees Celsius of additional temperature rise if we were to lose that umbrella. And you can take a screenshot now if you want to look more into the primary literature. I'll give 5 seconds. 5, 4, 3, 2, 1. Okay. Now, so this year has actually been and will continue to be a fruitful year for climate scientists looking at this issue. So these are data coming from the Netherlands, looking at the type and total amount of solar radiation reaching ground. Yellow, or orange, yellow, I guess, refers to direct irradiance, basically photons that come to the ground from the sun in a straight line. And diffuse irradiance are photons that got scattered somewhere in the atmosphere, changing direction and strike the ground at some angle. So, and superimposed on this graph is this dotted line, which represents, I guess, the lockdowns and resulting in a loss of this aerosol nanoparticle in the atmosphere. So we can see that, first of all, notice there's a constant profile going up. That's just because the seasons. There's more sunlight during the coming into spring, into the summer. So that slope doesn't mean too much. What you need to look for is that the fraction of yellow versus blue significantly increases when we lose the aerosol cover. That's because when there's less dust in the sky, you have less chances for the light photons to bounce and change direction. So you have the light coming straight down on the ground. So that's one effect. The other effect is you will notice that the fractional coverage by either direct or diffuse irradiance over the total available sunlight also increases. So in summary, this year, at least at this measuring station in the Netherlands, we have a record high in how much sunlight is striking ground. And both in the net amount of sunlight reaching ground and in the proportion of direct irradiance versus diffuse irradiance. And the amount of increase this year compared to previous years is about 2 watts per meter squared, which is very much consistent with model calculations of how much these this cloud is shielding the Earth. So now let's do some thought experiment in light of that discussion. So let's in each of these arrows trajectories, we're assuming that the world uses as exclusively one type of energy source. So in the gray, it's continuing doing what we have been doing, using coal, fossil fuel as our primary energy source. And the trajectory here, the red one, is assuming that this year we somehow instantaneously switch to solar thermal, concentrating solar thermal power, let's say. And the blue is if we switch to wind energy. So obviously, if we only look at CO2 axis, all is good. That's what you know with what you've been working on. We'll have less CO2 emissions. However, if we look at the temperature axis, the story is more complicated. So we know that losing this anthropogenic aerosol guarantees rise in temperature between 1 to 2 degrees Celsius. And we actually have a 90% confidence interval, more than 90% confidence interval that it will be somewhere between 1.8 to 4.5 degrees Celsius. Of course, all that temperature rise will not materialize overnight. About half of that will happen within the first 5 to 10 years. That's roughly the transient sensitivity of Earth. The remaining roughly 50% will slowly increase over the timescale of centuries. But nevertheless, if we stopped, say, fossil fuel today and somehow got renewable energy wish from a genie, where we will be above 2C within the next couple of years, a few years, with high certainty. Some people might wonder why wind is causing a higher temperature increase. So the reason is when wind turbines are turning, they're turning up the boundary layer. And during the night, ground level becomes cold because the ground radiates IR into space, and that's how it cools down. When you have wind turbines at the scale we're talking about, you basically have wind turbines everywhere, and then during the night, they'll continue to churn up hotter air at above boundary layer down to ground. So during hot summer nights, you will basically feel the same heat as during hot summer days. And for ecosystems, that's been demonstrated to be very much detrimental. So agriculture will certainly suffer, and human energy consumption will also increase as a result. Very recently, just a few days ago, I think even maybe at most a month, people used a simple climate model to ask the question of what happens if we stopped CO2 emission immediately. In this particular model, they didn't even include this aerosol effect we just talked about. So that's just assuming mechanisms that are being publicly discussed. So in two scenarios, one is we slowly ramp our emissions down over the course of the remainder of the century. The other is immediate stopping all emissions. So here is the temperature profile over the coming decades. So here again, in this model, they see an immediate decrease because they didn't include this aerosol effect. Just to look at the long-term feedback mechanisms. But it seems like regardless of whether we stop emitting, the future doesn't look bright for this civilization, at least on the longer term. And the impact is basically pretty much the same for temperature and sea level rise. And the difference fades over time due to intrinsic feedback mechanisms on Earth that kick in, like the melting of the poles and release of hidden carbon sources in organic form. So now, all that may sound hopeless, but I want to convince you that to the best of my knowledge, there's one solution, one engineering compatible solution that we still have left. But before, let's take a quick refresher on the heat balance. Basically, what determines temperature on Earth? We're basically a system in dynamic, right now, disequilibrium, but in history, it was more or less a stable climate because we had the same amount of light coming in versus the same amount of infrared photons going out in net energy flux units. But recently, we have slowed down the rate of escape by introducing more greenhouse gases, leading to an increase in the amount of heat trapped in the Earth system. So the way to fix that, we have two options. Either we open the outlet like we have been trying, or we can close the inlet a little bit. So either method should enable you to re-establish thermal dynamic equilibrium. So conceptually, these two approaches lead to very different engineering outcomes. So in the traditional approach to greenhouse gas emission mitigation, we are asking to filter the entire atmosphere, plus the ocean. That's a obligate 3-dimensional engineering challenge. If we were to just simply intercept some of the incoming light and send that back by reflection, it's a 2-dimensional engineering challenge. So here is just a summary of different strategies that we have investigated in our group. So the cartoon was done by Sky Lan, who's a high school student in New York City. So on the left, we have all methods that's based on intercepting the incoming part of the energy balance. And on the right side are methods that proposes to indirectly affect energy transport by drawing down these greenhouse gases. So all of these are not going to work simply due to the kinetics of the problem and the need for the gas to come into contact with whatever absorbing medium. So it's not really talked about in the literature, but if you're interested, please do the calculation for yourself and convince yourself that these are fantasies that need to be basically ignored, at least in the form that's depicted here. So the solution is to, instead of trying to draw down this CO2, which is a hopeless demixing process due to the energy of mixing, the entropy of mixing that's already lost in that process, let's cancel the heating of the CO2 using ground-based mirrors. It's very simple to calculate. What's the heating potential of 1 ton of CO2 when it's properly mixed in the atmosphere? It's 3 times 10 to the minus 12 watt per meter squared. It's also very easy to calculate what the cooling power of each mirror is per meter squared. It's 0.6 10 to the minus 12 watt per meter squared per meter of mirror. So to cancel the heating of 1 ton, we need roughly 6 meters squared of mirror, which can be sourced commercially at the price of about $10 US. But actually, if we have a global movement to implement this strategy, it's going to be much cheaper because the energy to manufacture this mirror is only at roughly $1 USD. And that's assuming $50 per barrel of oil, which we know can be quite volatile. So the price for canceling 1 ton of CO2 is somewhere between $1 and $10 US, which is by far the most efficient way to deal with this problem. So where should we put the mirrors? So here is a plot of the energy the Earth received in 2018 at the ground level, multiplied by 1 minus the local albedo. So the 1 minus local albedo parameter is basically what fraction of the light is being absorbed as heat. So ocean, you see, are a lot brighter because they absorb more of the heat compared to land, say the Sahara Desert, which is more reflective. So that's why, for example, oceans can be prime locations to implement mirror arrays to cancel out the heating effect of CO2. On land, we have other advantages. For example, you can tilt the mirror to a direction that's more orthogonal to the incoming direct solar radiation to get more, a trig factor of anywhere between like 1 to a factor of 2.5 on land. So actually, most of the land are also quite promising for putting up reflective mirrors for planetary cooling purposes. So as we looked more into the mirror strategy, we noticed, and we have so far developed multiple other renewable energy schemes that can be enabled by mirror and solar thermal technology. So here is a scheme where we can eliminate most of the world's or move most of our current carbon cycle to a net carbon neutral mean. So here, there's essentially 2 loops. I will first draw your attention to this calcium loop, starting from shellfish, becoming calcium oxide through a solar thermal decomposition, hydrolyzed to calcium hydroxide, and redispersed into the ocean to become a calcium ion, which then can be uptaken by these marine organisms. The second loop is the carbon loop. So the carbon in the carbonate becomes a CO2 under thermal lime formation, which can be reduced into fuel using electrochemistry that's been very actively developed, which then goes into the atmosphere, which gets absorbed by the huge expanse of ocean surface, and then taken up by the organisms. So let's do a thought experiment. Everybody switch to eating shellfish and oysters and clams to satisfy our energy need from the protein. First of all, we can save about 6 gigaton of emission from land agriculture. Next, the calcium oxide captured as a result of that aquaculture is equivalent to 1/2 of the CO2 emission we currently emit. And this calcium carbonate, when made into lime and hydrolyzed to produce heat, produce enough heat to heat more or less the entire world's housing heating demand. And thermal content in the CO2 off gas is enough to heat all the hot water needs that we have. Together, that constitutes a 9% reduction in fossil fuel use. So overall, this scheme alone allows 75% of CO2 emissions to become carbon neutral. And if the mirror infrastructure, in addition, are used to produce electricity by concentrating solar thermal, then we have actually a net drawdown potential without sacrificing fossil fuels, because it's just simply made to be a closed cycle. So with that, I'd like to conclude. So we have this project, it's being developed by volunteers from students from high school to grad school, and also postdocs who are volunteering their time to work with me. And I invite you to visit our website and also contact me for discussions, because we need all hands on board in this fight for our civilization, our species. Thank you.